Welcome to Study Loop.
Here's a nice little exercise to work with point charges and also demonstrate the difference between potential and electric field. So we have 2 point charges to start off with, separated by a distance d along the x-axis. And we want to find out where the potential total is 0. And to do that, we would have to add potentials from both charges. So we'll add those together using the point charge formula, which has the charge in the numerator with the constant k and the distance from each charge. So we have to ask, the distances are, of course, always positive that appear in the denominator. And let's just show what that would be. So we're only considering points along the line joining the two. So D1 would be, say, to the left of charge 1, and D2 would be taking care of that. Let's see, D plus D1 in this case, but it could be D minus D1 if it was in between. It really doesn't matter, but we'll see why in a little bit. The numerator in this case for both terms is always positive, and the denominator involving distances is always positive. And so there's no way for those two potentials to add up to 0 unless the observation point x is at plus or minus infinity. And that's kind of disappointing because we want to find points that are not at an infinity. Okay, so the potential cannot be 0 in a finite distance. Let's take a look at the electric field. So electric field can be added from both. And we usually have the charge with an absolute value. Again, there's a distance squared in the denominator. And then there's usually some little unit vector on the front of that to demonstrate that the electric field is a vector, of course. And points in the line from the source to the observation point. So let's take a look at some of the observation points. In between the two charges, what will happen is, let's call these two charges 1 and 2, so we can separate them out. The electric field from charge 1 will point to the right, and from charge 2, it will point to the left. And so if those are equal in magnitude, they will cancel. So that tells us that the electric field is 0 if D1 is equal to D2. And that means right in the middle of that distance separating them. If we look off to the side, of course, things aren't going to work. Then we have the electric field 1 pointing outwards to the right, and the same with E2. So the only place that the electric field can add to 0, provided you aren't at infinity, is right in between the 2 points. Okay, so notice the electric field can be 0. The potential cannot. And now as a second case, we're going to look at a positive charge for 1 and a negative charge for 2. And again, we'll put them a distance d apart. And again, ask, can the potential be 0? So let's take a look. V is equal to k positive q over distance 1 minus k q over distance 2. And of course, we see that that can be equal to 0 because the negative sign will allow cancellation. And that will be true if d1 is equal to d2. So smack dab in the middle between the two charges. Can the electric field be 0? And again, we want to think that we're really taking the absolute value of the charge, and the little unit vector is going to take care of the direction for us. So yeah, don't worry about the sign of that negative charge, but let's take a look at some examples. In between the two charges, let's see, the electric field somewhere in between. Let's just grab some point in between. For electric field 1, it will point to the right, and for electric field 2 as well. And so those are going to add together, and there's no way they can cancel. Let's look to the left of Q2. We do have the electric field pointing towards the negative and pointing away from the positive, but there is no way for those to be equal in magnitude because you're such different distances from the two charges. So there is no way the electric field can cancel to 0. So again, pointing out that potential and electric field are different. It's almost never true that one is 0 when the other one is also 0. Of course, there are special cases, but it's not a likely thing to occur. And again, you see a very different behavior if your two charges have the same sign versus opposite